Good evening to you. This is Galactic coming right back at you with the secrets of the universe. We've had our introductions for this day, so let's get into it. There are two ways to be sure that one is beginning on the right footing with geometry. One way is to go right back to the beginning. The other way is just to learn it all at once. I don't know if anyone has done that yet, so starting at the beginning is the only practical way to begin. The first thing we need to do is establish two theorems, which I have never heard described, so I can only assume that I discovered them. It is possible for a man to make a discovery for himself, not realizing it's already been discovered. This has happened countless times throughout scientific history. So it's not meant to be pretentious when I say that I discovered two theorems. I discovered them for myself, and now I share them with you. They're called the Antipodal theorem. These are my names, of course, since I can't find these anywhere, so I assume that I figured it out. But the Antipodal theorem is the way to begin, and from that, we can use another theorem that I derived, which I tentatively call the Bootstrap theorem. The first theorem, the Antipodal theorem, establishes that linear space is inherently embedded in spherical space. And that's a very specific relationship that I've established, which, if it's true, is incredibly profound. And since it is true, you're listening to the right person now. If you're interested in heavenly science from a rational point of view, such that you can understand the storehouse of knowledge that's been amassed with technology and the investigative minds of curious men about heaven, you need geometry now. That's the law now. That's the way it is. So no one's doing geometry. If they are, they're doing it in some cubicle somewhere using 2,500-year-old outdated theorems having to do with straight lines and a Lego grid that makes cubic space completely useless for cosmic science. The problem with using modern linear algebra with its calculus in cosmic space is that there's a big difference between the objects in heaven and the purposeful objects that we make with technology on Earth. On Earth we can machine things, which means we can match the machining of numbers to the machining of things. And it sounds so simple, but that is the basis of technology, and that's why we need calculus. It's because the universe is curved, and even on Earth, where we're much more familiar with square buildings and cubical things, because at our scale that does make sense to us, and we are hardwired to see linear space. So the gift of linear algebra and the gift of calculus are unrestricted for Earth. Untold wealth. There's no miracle in the Bible that even closely resembles the miracle of heaven's grace to Earth in linear algebra and calculus. The only problem, there wasn't a problem until we discovered the universe, and that was exactly a century ago, right at the end of the first phase of the Industrial Revolution. These are thumbnail sketches for topics that I've expanded considerably in the previous 200-some lectures that I've uploaded to YouTube. But it does need to be sorted before it can be indexed, and you would be able to look that up. But it is the province of science to summarize things. The lengthy part is the proof. The short part is the description with the explanation that provides understanding. That's what I provide. That's the commodity that I provide to science. To the best of my knowledge, nobody else on the face of the earth even gives a fuck about that, and no one is doing it. So, without making any apologies for that, although it would be helpful, I suppose, if that disturbs you, don't let it. Everything is going well. There's no actual problem except for a certain amount of human frustration realizing the potential of science, that it's not being realized. and the work of Sabine Hossenfelder, Dr. Sabine Hossenfelder, an astrophysicist out of Germany who's respected internationally now for extraordinarily good reasons. She's standing up to the system for the same reason that I do. And there are many people all over the world, professionals who are in industrial science, such as Sabine is, who are also attempting to point out the failures and faults and serious deficits in physics. That's not actually going to help physics per se, because physics has been commandeered by a higher power on Earth, governments. So there is a confusing situation right now in science. For rational, honorable, real people such as Sabine Hossenfelder and myself, and countless others who want science to progress, the situation is incredibly frustrating, because everyone can see that science, so-called, is nothing but pseudoscience, and it's holding everything up. Don't worry about that too much. Sabine is doing a magnificent job, and anyone who does this has the blessings of heaven, certainly in my eyes. That's unquestionable. Bravo, Sabine. I wish you all the best, but you're going to fail. And there's no way out of it. Okay? It's not judgmental. It's just facing facts. Science is irrecoverable now in the industrial sense, which is 99% of it. So don't be fooled by popularized science. It's controlled by the group mind. It's a conspiracy theory again, I know. But you're going to have to explain it some other way if you're not going to explain it that way. My explanation is absolutely dead straight on correct. And that's all you need to know. Give up. Sabine doesn't want to give up. Well, quite frankly, neither do I. I'm not going to give up. But you should. Don't fight this. The way to fight it is to correct it. And that's the big difference between Sabine Hossenfelder and myself. No fault of hers. No fault of hers. But it is a fact that she does not have an answer any more than these physicists do. And nobody has the answer. For that, we need geometry. And so we begin with the two theorems by which we can bootstrap true geometry. The first theorem is called the Antipodal theorem, that proves that the straight line is embedded in spherical space from the beginning. Use a Latin term, ab ovo. The way that this is proved is rather simple. You draw the line the same way it was drawn for us in school. It goes to two infinities, and from that you can deduce everything about the sphere. Because it goes to two infinities, you can create an Archimedean balance point in the center without numbers. It just has to be there because there are two infinities. And you'll see in a moment, in fact, let me show you why that's true. When you finally create the number system, which emerges naturally on the index system called the metric of the space, which in this case measures linear separation of distance. The unit for that, called the index in my language, is 0 to 1. But 0 to 1, being a distance of 1, on a line, has an opposite on the other side of 0. And therefore you have 1 and negative 1 that balance. Do the same thing with the infinities. And that, in a sense, cancels the infinities. What it does is it balances the line. This is a method that is attributed to Archimedes. If you're interested in that, I strongly suggest you look up Archimedes' proof of the area under a parabola. Archimedes invented the calculus. And he might not even have been the inventor. The calculus has been around as long as men have seriously tried to study curvature. Curvature is the problem. And here's how you get at it. First of all, you realize that we don't have a spherical geometry. The next thing you do is reconstruct the line the way... It wasn't Euclid who did that. He didn't know about the two infinities. Or that is, he didn't really talk about it, except in the parallel postulate. So that's why that was controversial for so many centuries, and in a sense still is. It's because of the fact that the line goes to two infinities. But if you take that line at the Archimedean balance point and rotate it in 360 degrees spherical, that the two endpoints end up hitting all the infinities. And that can be proved to be a sphere. There's no other shape that answers that geometry. And therefore the sphere is original, not the line. So the second thing you do is erase the line. Now we're done with lines, but this is an incredible theorem. You could say it has a corollary, which is that linear space is embedded in spherical space. We just proved it. And therefore the line and the sphere have a relationship. I'm going to show you what that is. It's incredibly important because the nature of the linear numbers that we do use, which I'm not trying to get rid of because that's impossible, but the linear numbers that we do use are computable numbers. Now, almost an infinite number of them are not computable. Conway proved that. But that doesn't matter because there are so many numbers on the line. It's the maximization of infinity such that it's still quasi-finite. And most of the numbers are extraordinarily transcendental, but they have something in common. They're irrational. But there are an infinite number of rational numbers mixed in, and those are the only ones used in geometry. You should accept that unless you're doubtful. That is, you should accept that if you see that only rational numbers work in cosmic space. Always remember that irrational numbers are no longer irrational on Earth because we can machine them with calculus to smooth out the corners and edges. But in cosmic space, you can't do that. And since the physicists haven't realized that yet, you should take a step ahead of them right now with me and understand directly why you can't use calculus to compute cosmic space. Do you see it? I'll spell it out for you. It requires a direct insight, so this is a contact with reality. So this will depend on, I suppose, your ability or capacity to see this, but I believe this should be obvious to anybody for whom geometry is going to have any significance at all. Is that the space that's in outer space, as opposed to going in, which leads to quantum mechanics, but outer space in the sense of going out, basically from the surface of the Earth, from where we're at, our reference frame, it goes out in all directions, right? True. Equally infinite in all directions. Now, since that's true for any point we can think of in the universe, that is a very interesting geometry. But when you just choose a point, such as the center of the Earth, which is a point, just say so, it's a geometric center is how you should put it, then going out is a specific direction. Well, as you go out, things get bigger. But way out there above the Earth, beyond the moon, beyond the solar system, what's the difference between that space and the space on Earth? You can't machine it. You can't pretend to change the numbers. Whatever the numbers are in the universe, they are not machinable because everything is complete. There's nothing to build. We're not doing technology with deep space. We're simply accepting it the way it is, and we have to understand the geometry, correct? Well, we're still using our numbers to interpret that space. That's okay in the sense that numbers are useful. However, nobody's realized that they're linear numbers computing nonlinear space. That's impossible. That can't be done. The reason for that is irrationality. An irrational number is not a number that the universe uses. That can be proved. We're getting to that. The second theorem is the bootstrap theorem, as I tentatively call it until I come up with a better name. Usually what happens is whatever name you come up with first, you're stuck with it. No, you can't change it afterwards because everyone gets used to it. Not much danger for that here. But we'll call it the bootstrap theorem. And what is that? After you've erased the straight line has done its job. By drawing it and analyzing it geometrically, you can prove that space is spherical and that the linear numbers are in spherical space. That's extremely important because the computable numbers are with us forever. As long as the linear space is embedded in spherical space, you can prove, using mathematics, that the number system of the superspace will inherit all the qualities of the subspace. That's critical to know. And if you don't know that, leave a comment and I'll see what I can do to answer that, but that is true. So now we want to bootstrap the universe, which sounds daunting, and so there will be a strange step, as there would have to be to bootstrap the universe, since in a sense you're trying to step outside the universe. And that's a good place to begin in showing how this theorem works. It's rather simple, but it's a bit more complex than the antipodal theorem, which is practically a direct vision without really any steps of proof. You draw the line, you recognize it hits two points in opposite directions, you rotate the line in every way that it can go, and you have your sphere. Now that's an unbounded sphere, which means it's not a space. A space has to be bounded, which leads to a question: is the universe finite or infinite? The bootstrap theorem will answer that question, and you should start to get used to that. The theorems and proofs that I'm going to be introducing to you in sequence now to get to our goal, which is we have quite a few steps to go before we get this fully, but you can see we're on the right footing so far. We've established that the universe is a sphere. Now, what is the number system for the sphere? In order to do that, you erase the line and start over. But we know that we have a center now, because the center of that line, no matter which way you spin it, rotate it around, it still has the same center. So we have that. And we have something else, infinity, the edge. So now we have two things in a space that we're trying to construct. We're going to say that those are numbers. And now we're going to use the Euclidean proof method by using axiomatic approach and creating postulates which we can prove, establishing our theorem. These are technical terms. They have somewhat overlapping meanings, but I'm attempting to use these terms in the way that they've been translated and interpreted right from Euclid. But be aware that these terms have changed. Axiom, postulate, theorem, they have variant meanings depending on a classificational structure. It's not too much to worry about, because usually the words make sense in context, but not always. It kind of was frustrating to me to get used to these terms, but now I use them habitually. So we're going to do it now. Here's the bootstrap theorem. You erase the line. You have a center. You don't want to call it a point, though, because it's not yet a number. And quite frankly, the point on the line is a linear point, and we're no longer in linear space, so we shouldn't say point at all. The point makes sense in context of the line. The center point for that is 0, but we don't want to assume that for the space we're constructing, and you'll see why in a moment. So we now assign two arbitrary numbers, one to the edge and one to the center, and see what we can do with it to construct space. If we say that the center has a numeric value, and we say that the edge has a numeric value, we're not really beginning in the same way we did with a line, are we? No, but we could have begun the same way with a line if we knew the balance point to begin with. If we knew that the balance point was 0, and we also knew we were going to have a metric, then the 1 and -1 balance on 0. And then 2 and -2 all the way to infinity, the two infinities balance on 0. That's also part of the antipodal proof. Is this the same? It's the same distance in both directions. Well, that would mean that one direction is the radius of a sphere, and the full line is a diameter of the sphere. And that is a proof. That actually proves that anytime you draw a line, the only way you're capable of doing that is by having original space, which is spherical. That's incredibly profound from a certain aspect. But let's continue. What we want is a number system for the space. We're not too sure of the characteristics of the space, except we can see that it's spherical. What else can we see? We can see that it has a center, and we can see that it has an edge. And now I'm going to show you something that I discovered, which is quite remarkable, that was never noticed until I noticed it. So you're going to learn something brand new right now. A discovery which I can only assume that I made, since I've never heard it stated, that the straight line has a number system with an operator. And it's just one operator, add. And without going into any further detail, because I've dealt with this in the last 3 lectures, the Archimedean balance point of linear space, that is not really... let me stop there. There's linear space, and then there's the linear system. And there's linear numbers, but there's also linear geometry. See, everything we do is linear, and so the names tend to overlap. But the linear space technically is the line, which is called 1D space. That's linear space. Those are synonymous. But the linear system is however many of those lines you're using. And so far we've tried 4. 1D space is the number system itself on the line. You can say that now. John Horton Conway proved that the number system and the object are identical in the sense that they're inseparable. So the line has an operator. In the next space, we want the next operator, or invent one if we have to. But we don't have to, because there's a free operator, because the line only has one operator, contrary to what we were taught in school. The next operator, you may have guessed, is multiply. But now we need to spell it out. Just as add has a linear valence of plus minus, that's going in opposite linear directions. That's plus minus balanced on 0 on the operator add, which now has an inverse called subtract. And so that's why that's really one operator, because they're both closed on the line, which means that whatever you do with the numbers on the line, you're going to stay on the line with add and subtract. Now that's also true for multiply, but it's not true for division. And so multiply and division, assuming that they're a pair, which I'm postulating now, I've already done this, but I'm repeating it for you, so I hope this is not going too fast. But that 0 on the line is called the additive identity, and so now you know what to do. The next operator, which is multiply divide, also has an identity number, and it's 1. So we're going to assume that that's the center of this space, because 0 is the center of linear space. Right? Good. So now we're going to say that 1 is the center of whatever space we have. But if it is the center, it's going to have to be between the actual center of the space, which is that what we were calling a point, but it's not a point anymore, it's just the center of the space. But you see we have a contradiction now, because we're saying that 1 is the center of the space. But now we can do a trick using multiply. And it's really the same trick that in degenerate form is implicit on the line. Forgive the highfalutin language, but you can listen to this tape more than once if you need to. And I'll also have publications in writing with diagrams to show this eventually. Hopefully by Christmas, but we'll see. Now, when you have the center and you have the edge, and now you have the middle of the space, it's going to be between the center and the edge. So now you can say that 1 could be what's in between the center and the edge, and that would be the center of the space. But there's a better way to do this, and I call this the bootstrap theorem. It does require a step which is so preposterous that you might balk, but I urge you to be patient, because it only takes 1.5 more steps, and then you'll see why we did things the way we did. So let's do it. We're going to assign 2 arbitrary numbers. to the center and to the edge. And remember that we're already convinced, that is, as a hypothesis, that we're looking for the number 1 in the space instead of 0, because 1 is the multiplicative identity, and we're postulating that multiplicative space may be for a separate object. So we're actually looking for the object, but you can see there's a skewing. From linear space, the center of the object is 0. But here, the center of the object is not really a meaningful term. We don't have an object yet. And if we did, it would be the center, wouldn't it? But let's not do that, because this is multiplicative space, and we don't want to do anything that would be constrained to the additive system. We need to conform to the space operator, is how I phrase that. The line is closed for add. What we're going to say is the object, I'll say it this way, the object for add is closed, and you can draw that as a line and it makes sense. What we want is the equivalent system using the same steps, but there is going to be a shift, and you'll see that that's what's kept this from being noticed. One of the reasons why nobody ever noticed that there's another object that uses another operator. And here's how we're going to prove that with the bootstrap theorem. We're going to say that the edge of the space is infinity, and we're going to define it as the space beyond the edge. Basically, it is the edge. That whatever is at the edge of space, inclusive of everything beyond it, which is unimaginable, is imaginary space. That makes sense intuitively, but we need to justify our step by showing its meaningfulness. And we're going to do so now by giving a reciprocal number to the center. And that's going to do something magic. Watch carefully. The edge number, which represents the entire edge of unbounded space. So this is kind of a magic step, and this is the difficult part. Bear with me. It's infinity over 1. There's where we're going to put the 1. Because putting 1 underneath infinity does not affect infinity, because we're taking one part of infinity. So infinity over 1 is the same as infinity, and that's already known. We're going to reverse that. That's called a reciprocal action, to put 1 over infinity. And what does that mean? It means the number 1 is divided in an infinite number of parts. That's the reciprocal of saying 1 part of infinity. So the edge is 1 part of infinity, and the center is an infinity number of parts that make 1. In other words, it's an infinitesimal, and that should alert you to something. To the same degree that the center may be considered a derivative number, the edge might be considered an integral number, and this will turn out to be true in my next theorem that I'll prove soon, probably the next lecture, but I'm bracketing what I'm doing so you see where it's heading. We make 1 over infinity the center number. That's less than 1, right? 1 over infinity is less than 1, but it's not 0. The number at the edge, infinity over 1, we have to define what infinity now is so that it makes sense in the relationship. Because these two numbers will multiply to 1 in the same sense that plus and minus infinity on the line add to 0. These are the equivalent of plus and minus infinity, but it's not plus and minus. It's multiply and divide. So in multiplicative space, as you might call this center is an infinitesimal, and the edge is the integral. Got it? That should make sense. It does make sense, except for one thing. We haven't defined what infinity is, and we need to do so now so that when we multiply these two numbers together, we know what they're doing. And they do two things when you multiply them together, because there are two numbers, correct? Yes. So the infinities cancel. And what does that leave? Imaginary space. We're saying that infinity is imaginary. It's not a real number. It's the number that's beyond the numbers. That's infinity. If you say that, you're going to find that you've now defined infinity, and this is the only infinity. And so all of the infinities discovered by Cantor are linear infinities. And John Horton Conway completed the work of Georg Cantor in that sense by showing that there are an infinite number of infinities, which is possibly why Georg lost his mind. But nobody knows. But he did lose his mind, and he died in a mental hospital. This is the man that was supposed to bring us paradise from which we'll never let anyone kick us out. I'm kicking you out. John Horton Conway stands with me on this, so you're out. There's only one infinity. It's the one that I just named. We haven't proved that yet, because we don't know how many infinities there might be. Yes, we do. There's one. But it has two parts, and this is extremely important. We already know that in order for us to interpret spherical space with numbers, it's going to have to be at least a two-component number. It can't be a one-component number because a sphere is a two-number object. Remarkably, so is the circle, and we'll talk about that in a moment. That actually doesn't make sense until it's spelled out. Why a circle could be parameterized with two numbers, but so can a sphere? It's actually because the numbers are defined differently. Also, a clue as to where we're going. These clues have always been in front of our eyes, but nobody's ever synthesized them into the number system I'm going to show you now. When you put 1 over infinity at the center of the universal space, and you make the unbounded edge of that space infinity, you can now multiply them together. And these are the two numbers that make the component numbers of a new number system. This was tried with complex numbers, but these are not linear, and neither one is imaginary. We already dealt with imaginary space, and by the way, that's also the only imaginary space. This is synthetic. This is getting rid of derivative solutions and replacing our derivative solutions with integral solutions. These will be rational, as I'll show you. With the center being 1 over infinity, the smallest of the small numbers, that is, the less than 1 but greater than 0, 1 over infinity is the smallest one of those. And that's the center of the universe. It's not 0. It's 1 over infinity. But that's actually not the center of the universe. And here's where it gets interesting. Watch what happens when you multiply 1 over infinity times infinity over 1. The two infinities cancel to imaginary space. And now you have a single axis, radial. It's a radial axis. I have to say it that way because it's not a straight line. It's all the straight lines at the same time out from a center. But when you say out, that's a direction. It's just all the lines that intersect the point, or try to, and go out and try to reach the edge. So all the lines stop before they reach the center of the space. You know where they stop? It's 1 over infinity. But now you see that all the numbers that we've made, you have the numbers over 1. These would be numbers you could think of going out, getting bigger and bigger, right? They're all over 1, but they're getting bigger. That'd be like, for instance, the smallest one with whole numbers would be 1 over 2. I'm sorry, 2 over 1. So you go, where are you going out from? You're going out from 1 over 1. That's the other number that's produced by multiplying infinity over 1 times 1 over infinity. The answer is 1. So what that does is it cancels the two infinities and leaves space with 1 at its center. but it's a different kind of center. It's actually a surface. And what is it? It's the number. It is a number. It's an object that's also a number. Now that's also true on the line. 0 is also an object that has a number if you consider the point to be an object. That's actually a mistake, but we don't know that yet. That's retroactive. It's kind of a corollary, a retroactive corollary of spherical space construction, that it gives us help in defining what linear 0 actually is. But now we have, instead of linear 0 at the center of the space, we have multiplicative 1. And it's not a point. What is it? It's in between 1 over infinity and infinity over 1. Infinity over 1 is greater than 1, and 1 over infinity is less than 1. So where's 1? It's in between. And if it's in between on a radial line going out in all directions, it's a sphere. It's the distance of 1 from the imaginary center to the surface. When the two infinities cancel, it generates a 1 in the middle of the space. And it's a sphere. With the numbers less than 1 inside the sphere, the numbers greater than 1 outside the sphere in pairs, all of which multiply to 1. Now we want the index of the system. This would be the metric, what it is we're trying to measure. What are we trying to measure on the line? It's distance. It's linear separation is the technical term. And since it's linear, it goes on a straight line. That's called distance. Technically, linear distance. With a balance point of 0 at the center and an index of 1, because that makes 1, then you can go 2, 3, 4, 5. It's just notches. What do we do in multiplicative space? It goes in two directions at once. This involves a mind split. Get used to that. Albert Einstein showed us we're going to need to do that. This is how to do it. When you multiply infinity over 1 times 1 over infinity, it leaves a sphere in the space and cancels the infinities to imaginary space. That's profound. That solves a couple of paradoxes that have perplexed young and old alike since the beginning of time. We'll circle back to that and show you why. But you're probably already seeing it, or certainly starting to see it. So now we have the number system of the space. It doesn't have any meaning yet, but it is coherent. Is it closed? Yeah. Any numbers that you multiply will stay in the space. For instance, if you multiply 1 over 2 times 2 over 1, it multiplies to 1. So the two numbers that are in the space multiply to the center. In the same way that the numbers we have in linear space add to 0, the numbers in this space multiply to 1. But with distance, you only use one number at a time. You measure from 0 to 1, that's one number, a distance of 1. It's distance 1, job done. You measured it, right? That's linear space. What are we doing in spherical space? We're measuring two directions at once. And so that's a little strange, isn't it? It is, but we're going to need something strange to break the deadlock in physics, and we need spherical numbers. We now have a sphere with a value of 1, and the rest of space is completely filled with numbers. Now, that so far does not vary from what 3D linear space does. It does fill space with numbers. It's just not spherical space. When you make 3 lines to fill space, the first 2 make a flat plane and the third one gives you depth. Everyone knows that. That fills space. But at the edges and at the center, it doesn't fit. It doesn't fit. It doesn't match. And so which one is original? Which is the best one? We just proved it. We need spherical space. And linear space is embedded. That means, and I'll show you that it does mean this, that the spherical numbers are calculable. They're computable numbers. We just haven't shown what any computation would mean, except for one thing, a number inside that's reciprocal with a number outside, that is, one is over 1 and the other one is under 1. Notice that this is a polarity relationship on 1. That makes inner space and outer space. What do those mean? We haven't said what that means yet. We're only saying that multiply and divide are closed. Can we prove that? Not until we have the metric. We can say that there are numbers, and we've said that there are two component numbers that multiply to 1. We have that. But what's the range of the component numbers? We know that one of them is 1, because we started out by making infinity proportional on 1. That's how we got the space. That's the bootstrap theorem. So everything is closed except we can't prove that it's closed for the operators, which is multiply and divide. Can we prove that multiply and divide are closed in the space? Not until we have the metric. That is, what is it we're trying to measure? Is it linear distance? No. What is it then? This is where it gets interesting. Without yet saying what these numbers mean, we are at least assured that so far we're being consistent. And now what we need to do is establish one more postulate, and that is to create the index of the space. The index for linear space is the distance from 0 to the unit number which we call 1. That makes 1 the first counting number. 0 is really the origin. It's not really a number. Just hold that thought. That's been argued for a long time, so don't try to settle it in your mind now. Just recognize that 0 is peculiar. You can see that, because every other number is in pairs. 1 and -1 all the way to infinity, negative infinity. It's balanced. But then there's one number that's it's either both plus and minus, or it's neither, or it's actually not easy to define. And therefore it causes an immense problem with division, and in fact, it cannot be done. It's completely undefinable what division by 0 is. That's the final proof that the multiplication division operator is not a linear operator. It is, in fact, a spherical operator, as we're beginning to see. But without the metric, you see, what we need is the first counting number. We know that the central number is 1, and that the split numbers, or the two component numbers, go in and out simultaneously, so that the 1 is constructed on these pairs, because they all multiply to 1. And so all the numbers multiply to 1. Perfect. They actually multiply and divide to 1. You have to say that because the two component numbers are division numbers, and you multiply the two division numbers together. But since they're reciprocal on 1, they have this magic property, which I'm going to show you later, is equivalent to the beginning of the Pythagorean theorem in spherical space, which will change a lot, very quickly. So we have the rudiments of a spherical number system. The numbers fill space, but we so far do not know what they mean, and we can't even construct them except on the rule. See, what we don't have is a definition of what the pieces mean. We know what 1 means, or we're assuming that it means what we're accustomed to it meaning, and so far that's been consistent with what we know about multiplication and division. No contradictions. But we're very well aware of what 1 means. It's distance. But what does this split number mean? Okay. In order to get at that, we have an incredible advantage from the storehouse of knowledge of humanity, and the man who is rightly attributed with the discovery of what helps us right now, the man who basically discovered the index of spherical space. His name is Max Planck. And you may have heard the other name for the index of spherical space. It's called the quantum. And here's what Max Planck discovered. He discovered that the quantum is the index of spherical space. Now, he himself would not have said it that way. He wasn't really thinking about spherical space. But we are. And what did he discover? He discovered an extraordinary relationship between two physical numbers. These are numbers that the universe has. What number might that be? It's frequency. Frequency is quantized. And this is actually how Max Planck discovered the quantum, was in analyzing the frequency wavelength relationship. And you may already know that it's multiplicative inverse. That for frequencies, say you have frequency 50. Frequency 50, you immediately know what the wavelength of that frequency is. It's 1 over 50. So, what did Max Planck actually discover about frequency? That there is a lowest frequency in the universe. That is incredible. That means that frequency is quantized. And what does that mean? It means that it uses human numbers. Beginning with what? Beginning at 2. 2, but it's not just 2. It's 2 over 1, which you know is synonymous with 2. And what's the reciprocal of that? It's 1 over 2. 2 over 1 and 1 over 2 are the quantum. That's the quantum number. It's the lowest number in the universe. If you count using the whole number. Every number over 1 is going to be a number, but we don't know what the top number is restricted to. Could it be a real number? Well, it can't. That's profound and blew the socks off of all of physics. Where physics, up until 1900, really, New Year's Day, just about, of the new century, Max Planck released very reluctantly his discovery that continuous processes, they were thought to be continuous, that frequency was of infinite range. It turns out that's not true. There is a lowest frequency, and that frequency is 2. And the other thing he discovered is that it goes up in quantum steps, so that after 2, there is no other number until you reach 3. But remember, there is a reciprocal number going down at the same time because of wavelength. So the lowest number 2 is actually 2 over 1 in relationship to 1 over 2. Well, so far, that could be our index, couldn't it? It is. That's what Max Planck discovered. The index of spherical space is 2 1/2. It's a two-component number that multiplies to 1. So wavelength times frequency equals 1. And that's the proof. And so now we have a coherent, closed number system for spherical space that so far doesn't really tell us very much. There are 2 reasons for that, each of which must be addressed, and I've already addressed them, so we're going back through those steps. What do these numbers mean? What is the metric? The metric for linear space is distance, which, as I just said, you should think of be more precise. It's linear spatial separation. That's what the line measures. What is the equivalent system of measurement? What are we measuring with the spherical space? Before we can answer that, we need to take a closer look at what Max Planck discovered about the quantum, because this is physical space now, it's not a mental construct. It's what the universe actually says about numbers that she uses. So this is ultimate profound. And this is why the quantum discovery is right up there with the greatest. I think so. I believe it's self-evident. There is another number system. In effect, Max Planck discovered another number system. Now, just to throw in something, just to tease your mind, perhaps, but I found this quite profound for me, is John Horton Conway, in his discovery of the correct definition of the number, the first man in history ever to define what is a linear number. He did so on a double null set construction, where on what he calls day zero of creation, you have no numbers, but he defines the structure as a two-component number. It's not a two-component number because the number doesn't really do anything, but watch what he did. On the first day, day zero, and don't worry, counting from zero is normal for mathematicians. It's really a meta step. It's the constructor, and it's a double null. In other words, the first two numbers in this space are double null. You'll see that is similar to what we were just doing with our two postulates to cancel infinities, was by pairing them. Either on add and subtract, you have two infinities plus and minus, they balance on the center point. On add and subtract, plus infinity plus negative infinity equals 0. And therefore all the other numbers from both directions going toward the center balance. And that's called the Archimedean balance point of linear space. The Archimedean balance point of multiplicative space is 1. We've discovered it's a sphere with a two-component number, one of which goes infinitely in to the proportion that their reciprocals go infinitely out. And that coherently defines space, thanks to Max Planck, who said that the index is the quantum number 2 over 1, 1 over 2, and the next counting number in physical space is 3 over 1 times 1 over 3. And this is the definition of the frequency wavelength relationship. But now comes a real mind bender, and it bent my mind and still does, and I hope it bends your mind too, because we're going to explain it fully, but it's going to take us a while. And after we're done analyzing what Max Planck discovered, a second discovery, independent really of his discovery of the quantum number system of the universe, a number system you and I have just composed for the first time in human history on an object that is not a line. It's the sphere. This is the gateway to the solution for physics. That is the new number system. And now we have to make it work. What Max Planck said, and we're going to close the lecture here at about 55 minutes. What do wavelength and frequency multiply to? We just said it's 1. It's obvious. Anybody knows that. It's not what Max Planck said. You know what he said that wavelength and frequency multiply to? Light speed. Look at that. Is that right? I don't argue with him, but I sure gave that a lot of thought. I leave that for homework for you, for your dream time. Think about it as you're going to sleep perhaps tonight. Why would wavelength and frequency, the lowest of which is 2 over 1 comma 1 over 2, that's the first wavelength frequency, those numbers are locked together to the proportion that frequency is 2, and it's never 1. It's never less than 2. It's either 2 or there is no frequency. That's very profound. That makes 2 the lowest counting number in the universe. But that's not exactly true. It's the 2 1/2 number. And 3 1/3 also multiplies to 1, so the number actually represents the sphere. All these dual numbers, one part of which goes in and one part of which goes out, when they're in reciprocal relation, as they are, then you have numbers that all multiply to 1, but the component numbers differ with a specific relationship between them. This is an incredible simplifier. If we can get this to work algebraically, we have our number system. So this is quite a motivator. But Max Planck said that that 2 over 1 for the frequency times the associated wavelength, which is 1 over 2, he didn't say that that multiplies to 1. He said it multiplies to light speed. That is pretty amazing. You'll see that. You can look this up in Wikipedia, Wolfram, anywhere else. They all have the same formula. 3 glyphs with an equator. The relational operation called equality between the left and right, just like with any other equation. But on one side, you have F, which is frequency, times what looks like a V, but it's nu. It's the Greek letter nu, which is shaped like a kind of a V, but it's curly. And that's wavelength times frequency. F nu equals, we say it's 1, Max disagrees. He says F nu equals C. That is a mind blower. That means that light speed in spherical space is 1. And that means that the surface of that sphere, the center of the space, in between the numbers going in and the numbers going out, which generate the sphere, that represents light speed. That's our key. That's our key. And I'll show you how that makes mathematical sense in the upcoming lectures going now for the next 4 or 5 weeks until Christmas. We're going to be homing in on the sphere. And to let you know where we're going, to close this out at exactly an hour, we have a static sphere. This is a geometrical object. All geometric objects that we've ever used are static. That is, they're not moving. They're just sitting there with kind of a freeze frame, right? That means it's not moving, static. So we have defined a typical geometric object, which until now there's only been one, the line, with a number system, but now we have 2. The sphere has a number system, and we know that linear numbers are embedded in it. I've just showed you where they are. They're the rational numbers. This system defines the rational numbers. These are by definition computable. So these numbers are fully computable as component numbers, which has not yet really been elaborated enough for us to be confident of making an algebra. In the next lecture, I'll show you how we can make an algebra out of that. But in order for it to even begin, something has to happen that never happened to the line. The sphere that we just created does not exist, because we already know from physics an attribute of all the spheres we've ever encountered, including the electron fermion, which within the past 10 years was proved to be perfectly spherical to a quantum degree of accuracy. It's as spherical as anything gets. That's a fundamental particle. Doesn't even have any moving parts. So really, one of the 2 central particles is a perfect sphere. By definition, the proton is a perfect sphere. And so the proton is a sphere, the neutron is a sphere, and when the proton generates the electronic orbital shells, which the electrons inhabit, it's entirely spherical in shells. That's exactly what we just defined, because you can see that from the surface of the sphere as a 1, to generate 2 numbers, or really the 2 generator numbers, the first counting number from the surface of the sphere goes out to 2 from 1 with nothing in between, and it generates an inner jump to 1/2 In other words, halfway to the center. The 2 goes out, and what does that make? It makes a shell. And the distance from the surface, which has a value of 1, it's actually 1 times 1. Actually, it's 1 proportion 1. The number that's now represented by an object, just as points are on the line, these shells are off the sphere going in and out, but with nothing in between. And this is called the quantum jump. That is the quantum jump. The initial quantum jump is from surface value 1 to surface value 2, in proportion as the other component number goes from surface value 1 to surface value 1/2. And now you have 2 concentric spheres, each of which took a quantum jump. Coordinated quantum jump. Does that sound spooky? This is homing in directly on the quantum paradox. And if you could see it right now, you might be capable of seeing the answer to the quantum paradox through strictly visual perception. That those quantum shells are going in 2 directions simultaneously. We can only see distance in 1 direction. So what is this other direction? You're going to find out, as I found out, and we're all going to know it together through proofs. Is it only one of those jumps, simultaneous jumps? Only one of them is linear distance, but the other one cannot be that. And that won't make sense until the next necessary step to complete my former sentence and to complete this lecture today. I want to say this right. Okay. In order to begin to understand this number system and its usefulness, we have to complete the sphere using a step that's never been done. And it's rather straightforward, but it's so fundamental that it's profound. And it is another I'm trying to remember the right word now. It's not a theorem, a postulate. And the postulate we're going to make now is a postulate you come back and prove. It's similar to a lemma, but more part of a different sequence. So I'm trying to do this in the Euclidean fashion, and I'm trying to explain and prove at the same time, always a dangerous occupation. You're either explaining or you're proving. But if you try to do both at once, it's a little tricky, so forgive me for floundering here for a moment. But what we're missing something. What we have is space, right? What are we missing? It's time. And we have to have that now. We know that from Albert Einstein, and really from Max Planck. We need time in here in the sphere. Well, where does that come in? Motion. It comes in with angular momentum. And so this sphere is rotating, and to complete my rather unfinished sentence, and to complete this lecture, and now I really do want to say this, right? The entry of motion onto the sphere is energy injection. That can be shown. And so what was missing from our sphere, you can say in 3 ways. We have space. We have numbers in space. They're not really doing anything for a good reason. There's no motion, because every sphere in the universe rotates. They all have a spin, and that's angular momentum, and that's extremely profound, because what we're missing on this sphere is obviously energy, because it's going to take energy to make the sphere rotate. But when you apply energy, you get motion. And from motion, you have the inherent concept of time. And actually, you cannot measure motion except in time. Whereas space requires no time, this sphere does require time. And that's where it is. We haven't said how it gets there yet, and that's in the next lecture. The energy injection event on the static sphere is the beginning of the universe. We only created the space for the universe with our prior two postulates, showing first that linear space is embedded in spherical space, also showing that spherical space is original, canceling the two infinities, ending the controversy over the singularity, and we're going to get to that by eliminating it, and answering the controversy over whether the universe is finite or not. It is finite. It's finite. And it's spherical. But it's a strange sphere because it's rotating, and that's also a discovery I made. The universe has an angular momentum component that has never been measured so as to know that that is what we were measuring. But I'm going to show you in the next lecture, we already have measured the rotational component of the entire universe. In order for this to even begin to make sense, we need the full geometry of the sphere, which does not appear until it starts to rotate, because the sphere has no real characteristics other than what it does to the space. It makes an inside, less than 1, and it makes an outside, greater than 1. That's good, but as soon as there's energy, it starts to rotate. And that changes the geometry of the sphere. It lights it up like a carnival tent, like someone threw a switch and all the lights come on. Because now you have a ring, and that's a circle. And it generates two other rings, which complete the sphere dynamically. They're two rotating rings, because as the sphere rotates, the other two perpendicular circles from the equator rotate like this. That's a relationship. And we now have a slew of relationships opening up because of energy injection. This is the entry of time. We're going to find time on the ring. We'll be right back.